All right, let's dive right into this incredibly structured look at the invisible digital infrastructure powering our entire world. Welcome to today's Explainer. We're going to break down our source material exactly in the order it's presented, step by step, to figure out exactly how classic internet protocols evolved into the massive Internet of Things systems that are literally surrounding us right now. Here is our roadmap for today. First, the rules of communication. Second, layered network architectures. Third, entering the physical world. Fourth, the evolution of IoT. And finally, bridging digital and physical. Let's jump right into part one. Section 1, the rules of communication. To understand these massive networks, we really have to start with the fundamental rules that get a simple message from point A to point B. So, what is a network protocol? It's basically a highly specific set of rules that endpoints use to specify how they interact. The absolute crucial point here is that without these protocols, our data would just be pure chaos. Your devices would be completely, utterly unable to understand each other or exchange a single piece of meaningful info. Think of this literally like the physical postal service. Before you drop a letter in the mail, you need a standard format, right? Like a standard envelope size. You need to pick a transmission speed, like choosing a priority stamp. You have to have a system for error handling, a return address. And of course, you need a backup plan for packet loss, just in case that letter vanishes in transit. Every single data packet embarks on a journey, and the protocol is the ultimate rulebook that answers the critical questions along the way. How is this message formatted? How fast is it going? What happens if an error pops up? What if parts of the message just get lost? The protocol handles the whole shebang as a digital package makes its way from device A to device B. Now, our source material categorizes these protocols, using a sort of sorting hat logic, into three main domains. First, we have internet protocols like TCP and IP running the web, then wireless protocols like Wi-Fi and Bluetooth built for mobility and variable speeds, and finally, routing protocols, which act as the specialized rules for network routers to hunt down the best pathways between a source and its destination. What's really fascinating here is how routing protocols dynamically identify routers, manage pathways, and instantly adapt when things go wrong. If a connection breaks, boom, it's just like a GPS rerouting you around a massive traffic jam. The network actively makes decisions to ensure your data still gets exactly where it needs to go. Section 2, layered network architectures. As networks exploded from simple one-to-one connections to global webs, engineers desperately needed a way to organize all these protocols without breaking the entire system. Which brings us to a huge foundational concept in computer science, cutting through overwhelming complexity using layered architecture. Layering is exactly like building a skyscraper. You handle the concrete foundation, the plumbing, and the interior design completely separately. It turns one massive, mind-boggling problem into much smaller, highly manageable pieces. The source breaks down the why behind this using three interlocking gears. First, it reduces complexity. Second, it standardizes interfaces, meaning completely different hardware from different vendors can interlock seamlessly. And third, modular engineering. Engineers can update one specific layer without having to rip out and rebuild the rest of the network model. It's brilliant, really. This layered logic naturally builds into the famous 7-layer OSI reference model. Data flows downward from the sender, starting way up at the application layer, dropping down to the physical layer like a fiber optic cable, and then shoots right back up to the receiver. It's the perfect open model for understanding these complex steps piece by piece. But let's look at a practical Rosetta Stone comparison provided in the source. It shows how the real-world TCP/IP model actually condenses those 7 OSI layers into a sleeker 4 or 5-layer framework. Notice how TCP/IP grabs all those upper-level user layers and squashes them into a single application umbrella, so it can heavily focus on the heavy lifting, the practical transport and routing underneath. Section 3, entering the physical world. Okay, keep that layered logic in your head, because we are about to leave the purely digital realm of computers, simply chatting with other computers, and actually step out into reality. Here is the absolute game changer we're exploring. The classic internet? That is entirely about moving data between computers. But the Internet of Things, or IoT, that is about applying logic to the real physical world. Think about a smart thermostat. That's a huge shift from just sending data to an inbox. It's actively sensing and physically altering the temperature of the room you're sitting in. It's a stark contrast.
On one side, you have the traditional screen-to-screen web connecting laptops and servers. On the other side, IoT demands completely new architectural blueprints so it can gather data from physical sensors like temperature gauges and cameras, transmit that data, and then apply physical changes back into the real world.
Section 4, the evolution of IoT. To handle this absolute avalanche of physical data pouring in from billions of sensors, IoT architectures had to evolve fast, stacking new layers of logic on top of each other. Let's see how that played out. Back in the early days of IoT, we started with a basic 3-layer architecture. You had a perception layer at the bottom, physically scraping data via sensors, a network layer in the middle, beaming it across, and an application layer at the top for the smart homes and user devices to see it. Pretty simple, right? Well, as millions of devices suddenly came online, that simple 3-layer model basically choked on the sheer volume of raw data. So the architecture had to shift into a 4-layer model by injecting a brand new data processing layer. This added processing units and decision engines to handle local analytics, crunching the numbers before the data could overwhelm the application layer above it. And that brings us to the mature 5-layer enterprise framework that's largely used today. It caps everything off with a massive business layer at the very top. This layer doesn't just glance at data. It manages entire system-wide operations, overarching business models, and ties the raw physical perception right at the bottom all the way up to high-level executive management. To seamlessly sum up that entire progression, the source lays out an evolution matrix. It perfectly tracks how processing power was shoved closer and closer to the actual data source over time, while the overarching business and system management was strictly locked in at the top level as things matured from 3 to 4 to 5 layers. Section 5. Bridging digital and physical. We've gone through the rules, the layered architectures, and the evolution of IoT. Now, let's tie every single piece of this together into one unified picture. This is the ultimate takeaway, synthesizing everything we've looked at today. The Internet of Things absolutely does not replace the classic TCP/IP networks we started with. Instead, it literally surrounds them. It uses those standardized modular layers as a transmission core right in the center, and simply bookends them: physical perception on one side and operational business logic on the other. Which leaves us with something pretty intense to think about. Seeing how incredibly fast we've jumped from basic air handling to these multi-layered, highly intelligent physical environments, as that perception layer gets even smarter, how far do you think these digital sensors are going to extend into your actual personal life in the next 10 years? It's a fascinating question, and one we absolutely need to be asking as this architecture keeps evolving. Thanks so much for joining me for this explainer.